So, good morning once more. Uh, Today, actually, we will start second chapter, which means we will be studying linear time invariant systems. In previous lecture and in previous chapter, we have seen some properties of the systems, right? So, starting from memorylessness property up to causality, we have seen many properties. Well, among two of them, actually, linear and time invariance are quite important for us. The main reason for this is this. Many physical systems are actually linear and time invariant. So we have to analyze this characteristic in details. Also, we will see that if your system is LTI and linear, it means that linear and time invariant. For this case, we have strong mathematical tools to study, analyze, and design such systems. And I hope this will be clearer at the end of this chapter. Well, we will first start with discrete time LTI systems, and it will be actually our first topic. First, we will start with stating that any discrete time signal can be written as a sum of weighted and shifted impulses. So it tells you that if you have x of n, actually you can write it as this form. So you can write your xn as, let's say, it starts, it may have infinite many terms, but so assume that we are just considering a few terms. So you can write it as x minus 2 times impulse of n plus 2 plus x minus 1 times impulse n plus 1 plus x0 impulse of n, and it goes on like this. So as an example, let's say I have such a system, such a signal, sorry. So I will write it simply as this. So here I have the first term. This is x minus 2 impulse n plus 2 plus I have the second term. So this is nothing but x minus 1 impulse n plus 1 plus I have the other term. It's right here. So this is x1 impulse n minus 1, and last term I have here the last term. So it is x2 impulse n minus 2. So I have decomposed the signal, my x of n. Well, it has actually 5 samples, and starting from minus 2 to plus 2, it has some values. And I have written them clearly as in this form. So this is my first term. So this is my very first term, and it is nothing but x minus 2 impulse of n plus 2. Then I have the second term, and it is here, it is x minus 1 impulse of n plus 1. And the third term here, x0 impulse of n. So remember, impulse of n is at 0. Impulse of n plus 1 is at -1. Impulse of n plus 2 is at -2. And what else? I have the fourth term. It is simply x1 impulse of n minus 1. And impulse of n minus 1 is at, of course, 1. And finally, I have the last term, which is x2 impulse of n minus 2. So impulse of n minus 2 is again at plus 2. So I can write this signal as the sum of 5 different impulses, so shifted and scaled impulses. So this brings us to this very, very important relationship. It tells you that if you have x of n, you can write it as sum of scaled and shifted impulses. So it is nothing but this formula here. So this is called as our shifting property. So it is our shifting property. So it is quite important in the analysis of impulses. Well, at this point, please remember our unit step signal. So what was it? Un was simply summation k from 0 to infinity, impulse of n minus k. So remember this. Well, actually, this is, so here you have the scale, which is 1. So x of k is 1 for unit step signal. So the rest is my scaled impulses. So this was just a reminder to you. So if I have an LTI system, so I want to find the input-output relationship for this LTI system. So at the input, I have x of n, and I want to find the output y of n corresponding to this system. Well, in order to define this, first I will start by writing the impulse response. So assume that at the input, you have the impulse, and at the output, you have the impulse response. Here, this is my input, and this is my output. So in general, this is my system. At the input, I have x of n. At the output, I have y of n. Well, if impulse is at the input, then h of n impulse response is at the output. If the system is time invariant, then what happens in this case? If the system is time invariant, then if I shift the input, then the corresponding output is also shifted, right? So this is the result of the time invariance. Well, what about linearity? Well, linearity tells you that, remember, if you scale and sum the inputs at the output, the corresponding output for this shifted and scaled inputs are simply the scaled and shifted, summed response of the individual signals. So if this is the case, well, if I simply write this as in this form, so this is the case. So if you simply scale the inputs by the weights of xk, then the corresponding output is simply again sk. So as here, so as a general, if I have xk impulse of n minus k at the input, at the output I have xk h of n minus k. So this is our result, right? So if I sum many of those terms and give as input to an LTI system, at the output I have simply scaled and shifted impulse responses. So this tells me that if you have xn at the input and yn at the output, it is simply k from minus infinity to plus infinity, x of k, h of n minus k. And this is in short denoted as this convolution cosine x of n convolved with h of n. So the idea is quite easy, quite simple. So you have a signal x of n, and this x of n is nothing but is written as scaled and shifted impulses. If your system is linear and time invariant, then due to time invariance, you can say that if I shift the input, the output is shifted by the time invariance property. If I scale the input and shift the input, output is also scaled and shifted due to linear and time invariance properties. So it's simple. If I sum the inputs, as in this case, which are simply scaled and shifted impulses, the corresponding, well, actually, this is supposed to be h of n. Sorry for this. So this is, since we are writing the output, this is nothing but h of n. So if I simply scale and shift the inputs, the corresponding outputs are also scaled and shifted versions. So when I sum those, I have nothing but the output for a corresponding input. Okay, so this is our case. Well, this LTI property actually for any given x of n, if you know the impulse response, you can find the outputs easily. Do it by using this convolution sum. So this is called as xn, or read as xn convolved with h of n, and this is the mathematical formulation. So let's write once more. This is the symbolic representation for the convolution sum. So I have y of n is xn convolved h of n, and this is the closed form expression. In this expression, h of n is called the impulse response and of this LTI system, and it is required to compute the convolution. So once more, if impulse of n is the input, h of n is the corresponding output. Okay, so this is our impulse response. And of course, by using the relationship that I have already shown, you can find the output y of n as the weighted and shifted impulses. So impulse responses. So this is due to the fact that actual x of n is nothing but scaled and shifted impulses. So in short, given any x of n, if you know the impulse response h of n, you can find the corresponding y of n easily. At this point, I have an example. So I have an LTI system, and impulse response is 2 times impulse n plus 1 plus impulse n minus 1, and I have the input x of n. We are asked to find y of n. So we will first start with plotting x of n and h of n. So this is my h of n. So h of n is, so this is at minus 1, this is at plus 1. So at minus 1, I have 2. And at plus 1, I have 1. And next, I have x of n. X of n is this, so this is my n. So it is 1 at 0, it is 2 at 1, and again 1 at 2. So these are my h of n and x of n. So I know that. So actually, what is x of n? X of n is impulse of n plus 2 impulse n minus 1 plus impulse of n minus 2. So I will find the input, find the output for all of those input cases. If impulse of n is at the input, I know very well that h of n is at the output. So let's plot this. So this is nothing but my h of n. So this is my h of n. Then I know that if 2 times impulse of n minus 1 is at the input, due to LTI property, 2 times h n minus 1 is at the output. So let's try to plot this. So what I will do, I will shift h of n 1 unit right, because it is h of n minus 1. So I will shift 1 unit right and scale by 2. So this is 4 and this is 2. So this is my 2 times h of n minus 1. And the last term, if impulse of n minus 2 is at the input, at the output I have h of n minus 2, and it is simply this. It is two units shifted version of the original h of n. So it is minus 1, 0, plus 1, 2, and 3. So if you shift this signal 2 units, then what is it? You have 2 at 1, and you have 1 at 3. So if you sum those signals, if you sum them, so note that y of n is simply sum of those 3 terms. So if you sum them, actually, let me write here. So minus 1, 0, plus 1. So my yn is, I have 2 at minus 1. I have 4 at 0. It is 3 at 1. It's 2 at 2. And finally, it is 1 at 3. So this is my y of n. Okay, so this tells me that by using this graph idea, or by simply representing the output as scaled and shifted versions of h of n, you can easily find the output. But in this case, actually, y of n is nothing but 2 times h of n, 2 times h of, sorry, it is h of n plus 2 times h of n minus 1 plus h of n minus 2. So this is my simple y of n. So the sum of those 3 terms. Okay. So this is the first way to solve the output for an arbitrary input. So what about the second case? In the second case, I will directly use the formal convolution sum. So the convolution sum tells me that if you have x of n and h of n, y of n is simply k from minus infinity to plus infinity, x of k, h of n minus k. So this is my very, very basic relationship. Then I will put everything in place. I have x of n. From x of n, I can find x of k. I have h of n. From h of n, I can find h of n minus k. So it is simply, I will only write k, but you know that the limits are from minus infinity to plus infinity. It is impulse of k plus 2, impulse of k minus 1. So this times 2 times impulse of n minus k plus 1 plus impulse of n minus k minus 1. So I have x of n, which is impulse of n plus 2 impulse n minus 1, and it goes on like this. So in order to find x of k, I will simply put k instead of n. So that's it. In order to find h of n minus k, I have this h of n here. So if you put n minus k instead of n, then you have h of n minus k, and it is simply 2 times impulse of n minus k plus 1 plus impulse of n minus k minus 1. So this is my relationship. Well, I will then write this. I will expand the summation term. So what is it? It is simply summation k So if I expand the terms, I have 2 times impulse of k. I have summation k from minus infinity to plus infinity, 2 impulse of k, impulse of n minus k plus 1, plus summation again k from minus infinity to plus infinity, impulse of k, impulse of n minus k minus 1, plus 4 times again the summation k from minus infinity to plus infinity, impulse of k minus 1, impulse of n minus k plus 1. And I'm continuing the terms plus summation k from minus infinity to plus infinity, 2 times impulse of k minus 1 and minus k minus 1 plus so in the second row again I'm continuing. I have 2 times impulse k minus 1, impulse n minus k minus 1 in the first summation, plus sigma 2 times impulse of k minus 2, impulse of n minus k plus 1, and the last term impulse of k minus 2 times impulse of n minus k minus 1. So these are my actually terms. So I will not analyze them one by one, but please note that, well, let's concentrate on the first term. It is multiplication of 2 impulses. What do I know? I know that if the summation runs from k, so if this relation n minus k plus 1 is 0, this expression is 1. So the impulse is 1. So if the input for the impulse is 0 in the discrete case, I know that the result is nothing but 1. So this brings me that k should be equal to n plus 1 for the whole summation to be non-zero. So the first term here is simply 2 times impulse n plus 1. So this is the first term. What about the second term? The second term tells me that k should be equal to n minus 1. So if k is equal to n minus 1, this summation as a whole is nothing but 1. So it is simply impulse of n minus 1. So you can go to all of terms in this way, and if you do this, you will find that this is 4 times impulse of n plus 2 impulse n minus 2 plus impulse n minus 1 plus impulse n minus 3. So I have those terms if I expand one by one. So for instance, what about this? So n minus k minus 1 should be 0, and k should be equal to n minus 1. So if you put here n minus 1, you have 2 times impulse n minus 2. So it is this term, okay? So I can further simplify this relationship. So how will I do this? Let's continue from here. I can further simplify this, and it is equal to 2 times impulse n plus 1 plus 4 impulse of n plus impulse n minus 1 plus 2 impulse n minus 2 plus impulse n minus 3. So please note that this is nothing but the results in here. So they both are equal. So in the first way, remember, I have done using this graphical solution and used the properties of LTI systems. In the second one, I have used the closed form relationship. And in this closed form relationship, if you go and solve the terms, you have exactly the same result. So you can use whichever you prefer. In the first one, I have used again the properties of LTI system. In the second one, I have used the properties of this impulse signal. And by using this property, I have easily get rid of those summation terms. And in the end, I have seen that both results, both solutions give me the same result. Well, the next example that I will solve is this one. It tells you that x of n is alpha to the power n un, and h of n is simply un. So what's the output? So in this way, I will use the closed form expression. Y of n is x of n convolves h of n, and it is this. If I write so, if I write the convolution sum, I have summation k from minus infinity to plus infinity, alpha to the power k, uk, u of n minus k. So, I know that this term is non-zero for k larger than or equal to 0. So this is a very basic property of unit step signal. Remember, it is 1 for k larger than or equal to 0. What about the second term? The second term is non-zero. It is non-zero for n minus k larger than or equal to 0. Or in other words, k smaller than or equal to n. So the first term is non-zero for k larger than or equal to 0. The second term is non-zero for k smaller than or equal to n. Of course, if I have the intersection, then for this term to be non-zero, k must be in the interval 0 to n. So I will correct the summation limits from 0 to n, alpha to the power k. And I know that this is equal to 1 minus alpha to the power n plus 1 over 1 minus alpha for n larger than or equal to 0, and it is 0 else. So this is the very basic application for the convolution sum. Well, in the second case, we will have the convolution integral. This convolution integral is actually somehow tedious to consider. First, note that I will define this impulse delta signal, which is equal to 1 over delta for t in the interval 0 to delta, and it is 0 else. So if t is in the interval from 0 to delta, impulse delta t is 1 over delta, and it is 0 else. Remember, this was our case when we were defining continuous time impulse signal. As delta goes to 0, this impulse delta is actually going to impulse of t. Remember? Then I will plot x of t signal and also x cap of t. So x of t is assume that my continuous signal, it has such a shape. And I've tried to find the staircase approximation to that signal. So I want to approximate the signal by some staircase representation. Of course, it is the same in the negative side. So I have such staircase approximation x cap t for x of t. So x of t is the continuous signal, and this staircase step-like representation is the approximate signal. So what is x cap of t? It is k from minus infinity to plus infinity, x of k delta, impulse of delta t minus k delta times delta. So I'm again summing the scaled and shifted versions of impulse delta t. So I have this impulse delta t. I'm simply summing the scaled and shifted versions. If you multiply impulse delta t by delta, you have unit amplitudes, right? Unit amplitudes, and you scale it by xk delta. So this is nothing but xk delta values here. So this is x of delta. This is x of 2 delta. So just like the discrete case, I'm scaling and shifting the impulses. Of course, now first I start with impulse delta, then I will show that x of t is nothing but as limits delta goes to 0, you have x cap of t. So it is limit delta goes to 0, k from minus infinity to plus infinity, x of k delta, impulse of delta t minus k delta and delta. And it is nothing but in the limits. So this delta is going to 0. So this is my just like differential term. It's just like my the delta term. This is going to again the impulse signal. And again, since delta is going to 0, I have here integral from minus infinity to plus infinity, x of tau, impulse of t minus tau d tau. So the summation is going to integration as delta goes to 0. So this tells me that actually x of t is nothing but integral x of tau, impulse of t minus tau, and d tau. And the limits are tau from minus infinity to plus infinity. Well, this is actually a quite important property called as the shifting property for the discrete case, for the continuous case. Remember the deal for the discrete case. So, and this is the shifting property for the continuous case. So just remember our deal for the discrete case. Now we will try to find the outputs for any signal, let's say x of t. In order to do this, first I will define impulse delta t. If you have impulse delta t at the input, assume that you have h delta t at the output. Of course, again, by time invariance, I know that if I shift the input, the output is again shifted. Okay. Again, by using linearity, if I scale and shift the input at the same time, then at the output I have x of k delta, h of delta, t minus k delta. And I know that x cap of t is this. So if this is the input corresponding output y cap is written easily using the properties of LTI, x of k delta, h of delta, t minus k delta times delta. And I know that as delta goes to 0, y of t, x of t, x cap of t is going to x of t, and y cap of t is going to y of t. So this is my note. Then as delta goes to 0, then I have y of t is simply integral from minus infinity to plus infinity, x of tau, h of t minus tau d tau. And where, of course, impulse of t has the response h of t. So this is our convolution integral. Actually, this brings us to the convolution integral. And in this case, actually, if you have any x of t, then you can find the corresponding output y of t by using this convolution integral. Of course, you should know h of t, which is the response of the signal for the impulse input. And h of t is our impulse response. Well, once note that if we are talking about impulse response, h of t, convolution integral, then you are working with an LTI system. All of the properties for the discrete case and the continuous case regarding convolution sum and the convolution integral are valid for linear and time invariant systems. Okay, so this is our case. Well, the output y of t, of course, can be interpreted as the integral of weighted and shifted impulse responses, where the weights are given by the input sequence x of t. The convolution integral can be used to compute the output y of t for a continuous time LTI system with impulse response h of t for an arbitrary continuous time input signal x of t. So it tells you that if you have h of t for any input x of t, you can find the output by using convolution integral. Well, at this point, I have an example. It is ut minus 2, h of t is ut. So what is the output if x of t is input to the system? Of course, it is the convolution integral. So we are asked to find y of t, which is integral from minus infinity to plus infinity, x of tau, h of t minus tau d tau. Let's plot x of tau. So what is it? It is ut minus 2. It is x of t. X of tau is u tau minus 2. Of course, it is 1 in the interval 0 to 2. What about h of tau? H of tau is actually nothing but u tau. It is this. So it is going to infinity. Well, in convolution integral, I will multiply and integrate x of tau with h of t minus tau. So I will find, or I will plot h of t minus tau. It is scaled and shifted. So I scale and shift the time index. So this is my h of t minus tau. Due to this minus, I have time reversal. So the graph extends to minus infinity, and this t is giving me a shift. So this is my h of t minus tau. Well, I will multiply x of tau and h of t minus tau. So let me first draw x of tau. Remember, this is my x of tau. It is from 0 to 2. Okay, it is 1. Then I will plot h of t minus tau. So this is h of t minus tau. Well, note that if t is smaller than 0, those two signals have no common area. So if t is smaller than 0, I know that the multiplication is 0. So y of t is nothing but the multiplied and integrated signal. So y of t is simply 0 in this case. If t is in the interval from 0 to 2, then it means that, let me erase this part. Then in this case, if let me draw once more. If t is in the interval 0 to 2, then it means that this is a number from 0 to 2. So it is just like this. I have t here, and this is my h of t minus tau. So what is the multiplication of x of tau and h of t minus tau? It's nothing but this area, right? So what is the integral? It is y of t is integral from 0 to t, because the multiplication is only non-zero from 0 to t. The value of x of tau is 1, h of t minus tau is 1, and I have the tau, which is simply t. Okay, so if I increase t, you see that the area under this multiplication is increasing. So if t is larger than 2, then of course I have this full area here. So y of t is simply integral from 0 to 2 d tau, which is equal to 2. So if I want to plot y of t, it is 0 for t smaller than 0. It is increasing, right? And it is constant for t larger than 2. So this is my y of t, which is the convolution of x of t and h of t. So here you have an exercise. So please try to solve this exercise by yourself. And in the next week, I will start with solving this example. So let me stop recording.